All right, welcome to the show. The clock shows 40 minutes, but that's a lie. That's what Big Pharma wants you to think, but no. The last 10 minutes are just for Benedict and myself to make some announcements. But the last talk of the first day, and it's with great pleasure that I'll revisit some of the memories from 2017 when I think Jonas started working on this project with Nima. And so, yeah, our last speaker of the day is Jonas Frey, and he will speak about coproducts in infinity locally Cartesian closed categories with subobject classifiers.
Thank you, Chris. Yeah, I was unsure whether I should go into the history, but I guess now I can explain it. So, yeah, we started working on this project a few months after Mike made this proposal of a definition of elementary infinity topos. I think I looked it up. So Mike posted this on the N Cafe in April 2017, and then a few months later there was a MRC meeting close to Utah where Nima and me started working on this, and we figured out a construction that I will present pretty quickly, but then got stuck in the proof, and then because of geographic issues, we didn't continue it on with it very intensively. But anyway, now finally we figured out how it works, and the proof is actually pretty easy. And so, yeah, and thanks to the referees for their comments. One of the referees pointed out that it's not clear what the difference is to what I'm about to show you and the proof that elementary one toposes have finite co-limits. And I thought that's a good point, and I will therefore start by looking at the one topos situation and discuss the differences, and hopefully get to an intuitive understanding of our construction from there. Okay, so context. In the end of the 60s, I think 69, Levy and Tierney came up with the original definition of elementary topos, which included explicit requirement of finite co-limits. I gave two citations here, one from Levy 1970, Tierney 72. And so Levy says, topos is a category E which has finite limits and finite co-limits, is Cartesian closed, and has a subobject classifier. And Tierney says basically the same. So soon after, it was figured out that the co-limit axiom is redundant. Michelson gave a talk in 72 in Oberwolfach, where he made this observation. Paré then came up with a nicer proof that was published 74, and Michelson then defended his thesis, I guess, in 76. Probably he was, I assume he was maybe a student of Anders Koch, I'm not sure. And then that's where his proof is written up. So, so let's quickly have a look at Paré's proof. What Paré does is that he looks at the autoadjunction of the contravariant power set functor. So homing into omega, taking internal hom into omega, into the truth value object in a topos, gives us power objects. And in any Cartesian closed category, we always have this adjunction that homing into any object is kind of a Galois connection, a contravariant self-adjunction. And so what Paré observed is that this autoadjunction is actually monadic. And that means that E-op can be presented as a category of algebras for a monad over E. And E has finite limits. And this is inherited to categories of algebras for arbitrary monads. That means E-op also has finite limits, and therefore E has finite colimits. So that's a very clever proof. But it's, bit of a black box, and I don't get a really good intuition out of it. So I'm going to show you another proof, or kind of a sketch of a proof that is, I always found more intuitive, and I mean, where you really see what's going on. So we call this the internal language proof. And I don't know if that's the argument that Nicholson also suggested. So the idea is that we know that so if we know that in elementary toposes we can model intuitionistic higher order logic, then we can just pretend that we are working in some kind of set theory, and then we say the initial object is the least subobject or subset of the terminal object. So that's the set of all elements of the terminal object such that false. And the more interesting part is how the binary coproduct is encoded. And the binary coproduct is encoded is the set of pairs U, V, where U is a subset of A and V is a subset of B, where exactly one of U and V is a singleton and the other one is empty. So this hash symbol means cardinality. So either U has cardinality 0 and V has cardinality 1, or the other way around. And then there's a construction of co-equalizers, and that's a bit more involved. So if you have two arrows, then parallel arrows take the image factorization of their pair, form internally some kind of reflexive transitive symmetric closure, take the characteristic map, take image factorization of the characteristic map. But I'm not gonna, we won't need this in the later part. So for this to work, we need some kind of first order logic that we can do with subobjects. And so as soon as we have power objects and we can do first order logic with subobjects, meaning monomorphisms, then these encodings work. So how do we get first order logic with subobjects? Well, it turns out there's a very clever encoding which we only need a conjunction, equality, and subset comprehension or abstraction, and then we can encode all first order connectives. For example, for propositions P and Q, the implication is encoded as P and Q equals P. And then for all x, Px means that the set of all x such that Px is true with is equal to the set of all x such that true, and so on. Sure. Yeah, we'll come. Yeah, so let's just talk about the other ones. So the false is for all z. I should have called this P. So that's just the universal quantification of over all truth values, and then disjunction and existential quantification are also given by these impredicative polymorphic encodings. And you might also know them from system F, if you know system F, or from the calculus constructions. They are all the same encodings can be used. Okay, so let's come to elementary infinity toposes. So Schulman proposed this definition that an elementary infinity topos is a locally Cartesian closed infinity category with finite co-limits, a subobject classifier, and enough universes. As soon as he suggested that, obvious question, is the finite co-limit assumption redundant again? Well, we have a partial answer, namely we can construct disjoint finite coproducts from only from the LCCC structure and the subobject classifier. We don't use universes. Okay, and now I'm gonna discuss the proof and try to motivate it by comparing it to the one category proof. So first, let's talk about the logic of subobjects in infinity locally Cartesian closed categories. So first of all, what do we mean by subobjects? A subobject is also known as embedding. It's just a -1 truncated map or equivalence class of -1 truncated maps into a fixed object. And I guess you don't have to say equivalence class if you assume that everything is univalent. And that's the nicest setting, I guess. So we can construct, we can take the sliced category of E over any object, and then we take the full subcategory on -1 truncated maps. It turns out that it's a poset in the sense that all homes are propositions, and the local Cartesian closure of E implies that this poset is Cartesian closed, and Cartesian closed posets are called Heyting algebras. Furthermore, so in any LCCC, given a map F from B to A, we have the pullback map, and it has a left adjoint given by composition and a right adjoint, and that's just the definition of LCCC, that these right adjoints exist. And it turns out that so the pullback and the pi restrict to subobjects, just because pullbacks and pi's of subobjects are propositions. So, well, in type theory, the pullback stability is kind of for free, and the stability under pi of propositions is something that is proved in the whole HoTT book. Okay, so now let's talk about subobject classifiers. So the pullback action that mapping A to the poset of subobjects is contravariantly functorial, gives rise to a functor from the opposite of E to posets. And so it turns out that this is actually a subfunctor of the functor that sends A to the slice category, which goes into infinity categories. And in both cases, we have the core functor. So the core of an infinity category is the infinity group weight of isomorphisms, which is we can view as a type. So we write S for spaces. And it turns out that the core of a poset is always zero truncated, so it's a set in a sense. So a subobject classifier is an object that represents this pre-sheaves of zero types, a core after sub. And because it represents a pre-sheaf of zero types, it's itself a zero type. And well, the representability condition means that there's a generic subobject of omega, such that every subobject of an arbitrary map corresponds to a unique map from A to omega via this pullback action. And as in the one topos case, we can show that the domain of the generic subobject is terminal because it classifies maximal subobjects. Okay, so it turns out that we can do, I showed you these these higher order encodings of first order connectives in one toposes. It turns out that exactly the same works in locally Cartesian closed infinity categories with subobject classifier. And so I've rewritten the encodings of the falsity and disjunction, which corresponds to finite joins in the subobject lattices. And again, the smallest subobject of any A, so the falsity, is given by taking the generic predicate times A and then pushing it forward along the projection back onto A. And then for the disjunction, it's again the same formula. And if you've seen it, you believe me, and if not, I can't convince you in this short time. So image factorization also works, but we don't need it. So image factorization would correspond to existential quantification. Okay, so with that, we can almost prove that we have initial objects. So first we prove a lemma. The lemma says that if I have an object J of an infinity locally Cartesian closed category E, then the following are equivalent. Either the subobject lattice is trivial, or the slice category is trivial, or the object is initial. The proof's pretty easy. If the object is initial, then every subobject has to have a section, because otherwise, well, by initiality, there has to be an error in the other direction. From the triviality of the subobject lattice, we can conclude the triviality of the slice category by this trick using this is-contra argument of Wygotsky, that we say if we have an object of an LCCC, then it is contractible if and only if a certain proposition is contractible. And so if all propositions are contractible, then all objects have to be contractible. And finally, to get from 2 to 3 to prove initiality, so given we have to show that for any a, the exponential object a to the j is contractible, so meaning there's a unique map from j to a internally. And the exponential can be written as a pi, and that's a pi over something that by assumption has no non-trivial subobjects. It has no non-trivial maps into it. So we know by assumption that this map is contractible and pi preserves contractibility. So that's pretty straightforward. Corollary, any infinity locally Cartesian closed category with subobject classifier has an initial object, because we can just take the least subobject of the eternal object, and that won't have any other subobjects. Okay, so now let's come to the more interesting part. That's the coproducts. Let's have another look at the construction in one topos. So I've written out this encoding again. How can we understand that? So in a one topos, or in set theories, think about intuitionistic set theory. For any set A, we have an embedding into the power set, which maps every A to the singleton. And now here I have a pullback square where on the bottom I have this embedding, and then I have the empty set is also an element of the power set, and it turns out that the empty set is different from all the singletons, and therefore we get this pullback. And now, for any A, I can form this construction. So given an A and a B, I can form the transposed product of these two pullback squares. I get this, and that shows me that I have disjointly embedded A and B into a larger object. Now, using the finite joins, whose existence we've proven using these impredicative encodings, we can form the join of the subobject A and B in the larger object, and then prove that this join is the coproduct, basically. And so that's how it works. And that can't work in higher categories for the simple reason that omega is a zero type. So omega of A will always be a zero type. So we cannot expect to embed arbitrary types into zero types. This can only work for zero types. So the exact technique doesn't work, but it turns out that we can do something very close. And so before explaining you how that works, let's talk a bit about two-category or infinity two-category theory. So I've shown you for any map from B to A that we always have this chain of adjunctions between pullback, sigma, and pi. And now it turns out that if M is an embedding, then sigma M, sigma and pi along M are fully faithful. The proof is also easy because sigma is the post composition, and it's pretty immediate that post composition between the slice categories is fully faithful if the map is an embedding. And then if the left adjoint of an adjoint triple is fully faithful, then so is the right one by an argument with mates. So you can do some transposes of squares of two cells, and then this falls out. And in particular, why I tell you this is that if I have an embedding and I have a map into the domain X into A, then I can take the pi, the push forward, and can pull it back, and I get the same thing, because the full faithfulness means that the adjunction is a reflection, and that means that back and forth, or forth and back, is equivalent to the identity. Okay, so this square is what we need. So let's move on, and let's take an arbitrary A in infinity LCCC with omega.
Generally, let's move quickly, if I may.
Pardon?
In general, when we're moving, let's move quickly. Quickly forward is what I'm saying.
Okay, I will quickly continue. Is that what you're saying?
Yeah, quickly, yeah. Good.
Okay. So let's take an arbitrary object in infinity LCCC. Let's take the push forward along the generic subobject, along the true map. And let's take the pullback again. Then we get this square that I drew in the front of a cube. On the bottom, I have another square that is the classifying square for the least subobject of 1. So take the least subobject of 1 here, and that has a characteristic map false here, and then this lower square is a pullback. Then we form the pullback of these two pullback squares in the arrow category. We get the cube because pull limits in arrow categories are component-wise. The two side squares are pullbacks, and by the pullback lemma, all the sides are pullbacks. In particular, the top side is a pullback. Furthermore, I is initial because 0 is strict, and then by the back-Chevalier condition, the back square is also a push-forward square along a monomorphism. So that, and this is an equivalence, so this also has to be an equivalence, so J is 1. So we get this square on the bottom, and again, we have embedded A disjointly into a larger object, A bar, with a disjoint point, disjointly embedded point. So it's important that this is also an embedding in this, because this thing is a pullback square. And points of omega are always, points of 0 types are always embeddings. Okay, and I should mention that this A bar is also called the partial map classifier or partial map representer. So, okay, so now what we can again do this for two different things. A and B form this product of the transposed product, get A and B embedded, form the join C in subobjects of A and B, get such a cospan of embeddings whose intersection is empty. And now what remains to be proven is that this is indeed a product cospan. And so what we show is that if we have such a span such that with two subobjects whose join is top and whose meet is bottom, then this is a coproduct. So, and now I'm quickly gonna give you a sketch of the proof. Basically, we write down the universal mapping property of the coproduct and observe that it means that the pullback of sets of this diagram is contractible. The pullback of spaces, not sets, of spaces of this diagram is contractible, but that's the image under global sections of this cospan in E. So it's sufficient to show that the pullback of this is contractible in E. And it turns out that we can write this type theoretically like this. And then, so we have to show contractibility of this. And since we have, and I forgot to say that I assume without loss of generality that C is terminal, because we can always do this because the sigma functor always preserves colimits. And this simplification was suggested by a referee. Thank you for that. Anyway, now we can argue by cases, and then by some simple type theoretic argument, that's true. And I leave it at that. Thank you very much.
All right. Thank you very much indeed. So let's have a quick applause here in your favorite form. And we'll open the floor to questions. You can write your question in the chat, or you can try to raise your hand. And Claudia will surely inform me of that, and we will let you in and join the live stream. So, yeah, raise hands. Even when you raise your hand, also write in the chat, just so that I know that you may be raising your hand. Okay, we'll wait a couple.
Just a comment. Do not forget to click on I'm ready when you raise your hand.
Oh, you have to click on something? What was the...
Click on raise your hand, then click on unmute yourself and click I'm ready. Then
I'm ready. Okay, yeah, so it's very,
I will send an email to everybody today so they understand the dynamics, because it's quite hard.
Okay, so when you're ready, raise your hand, unmute yourself, and then say that you're ready. It feels exactly like in a in-person meeting. When you want to say something, you have to do 3 things before you say it. Okay. I see no hands. So before we conclude today, I'll thank Jonas again for this great talk and a piece of history of topos theory that I was not aware of. Before we adjourn, I'd like to thank Malina and Alejandro, who have been with us for this whole session to troubleshoot. Oh my God, Peter just raised his hand. So, Peter, you're in. Peter? Peter!
Hello. Yeah.
Hi.
Oh.
You're muted again. You could just. There you are. Again muted. Unmute yourself.
That's just like dealing with Peter in real life.
As you said, Clouder is just for like real life. Thanks, Jonas, for a very nice talk.
Thank you.
So I was going to say, something that sort of seemed to show up in passing, but you didn't quite mention or didn't highlight, was that the version for the 1 and the infinity cases comes back to having the higher order encodings of the sort of coproduct-like, colimit-like connectives in the -1 case.
Exactly. Yeah, on propositions.
Right. So that sort of right. That even seems like a -1 level version of the same result. That somehow can one unify the proofs of the -1 case and the 0 case, or does the 0 case inherently depend on the -1 case? Do you know?
Well, I mean, -1 is special because there we have impredicativity, and we are really using that. I don't know if there's much more. I don't have any much more to say on that.
Right. Yes. Sorry. Not a very clear question, but just kind of seeing if during that thread had been something you had anything to say about.
I mean, a related issue, of course, is if you want to impredicative, non-truncated universes, but that's an exciting topic for future research.
All right, maybe I'll just say thanks to the organizers of FSCD for helping us throughout the session. And we resume in 18 hours in the same room. And we'll see you all then. So thanks a lot and enjoy your evening.